Welcome back to this next video in which we are discussing fraction fields. Okay, so we've now seen the set that we're actually going to use as our fraction field. It's going to be the set of all the equivalence classes of fractions where the numerator and denominator are from our original domain capital D, and those equivalence classes, remember, contain loads of fractions which we want to be considered equivalent to one another. Okay, and it's this set of all of those equivalence classes that is going to now form our fraction field. Okay, so what we now need to do to turn it into a field is define an addition and a multiplication law on this set of equivalence classes, and that's what we're going to do now. Okay, so we'll start off with addition. Now hopefully this should remind you, or at least you should recognize the way that I'm going to define addition as the way that you've been adding fractions for years and years and years. Okay, right. So what I'm going to do then is take one equivalence class. Okay, so I'm going to take the equivalence class that contains the fraction a over b. So I'm going to take a over b bar, and I want to define what it added to another equivalence class of fractions, and we'll have the equivalence class that contains the fraction c over d here. I want to define what this addition is going to be. So this is addition in my fraction field to b. Okay, so this is the addition that I'm defining. Okay, now, how am I going to define this then? So the way you're going to do this is you're going to take a representative from this equivalence class, you're going to take a representative from this equivalence class, and you're going to use their numerators and denominators to construct a new fraction, and then you're going to take the equivalence class that contains that fraction. Okay, so you might as well use the representatives that we've got sitting in front of us, but you don't have to, and that's one of the first things we're going to have to make sure is true, that it doesn't matter which representative you use. Okay, but we might as well use this representative here, a over b, and this representative here, c over d. Okay, so we're going to use their numerators and denominators to construct a new fraction, and the way we're going to construct a new fraction is we're going to take a and multiply it by d in the original integral domain. Okay, we're then going to add it in the integral domain to b multiplied by c, and then we're going to put that over b multiplied by d. So all of these operations are done in the initial integral domain, so I might just colour them in green. Okay, so where you've got a green operation, that means in the integral domain. Okay, so red is for the fraction field, green is for the integral domain. So you've taken this fraction and this fraction, which are representatives of these equivalence classes of fractions, and you've used their numerators and denominators to construct this new fraction here, and then the answer isn't going to be the fraction, but instead is going to be the equivalence class that contains that fraction. Okay, so you take a representative from here, you take a representative from here, you use them to construct this fraction here in exactly the way that I've shown you for this representative a over b and this representative c over d, and then you take the coset, sorry, not the coset, the equivalence class that contains that fraction. Okay, now this is going to be a fraction is the first thing that I should say. Okay, and the reason it's always going to be a fraction is that what we will end up with on the top is always going to be an element of our initial domain, capital D, and what we end up with in the bottom is always going to be an element of our domain, capital D, and it's never going to be 0. And the reason it will never be 0 is because b and d were never going to be 0, because remember, you never have 0 in the denominator, and in an integral domain, when you multiply two non-zero elements together, you'll get another non-zero element. Okay, so that's why we can be sure that you will get a fraction in this way, and then you just take the coset that contains, sorry, I keep saying coset. If I say coset again, replace it with equivalence class. Okay, for those of you who have studied other abstract algebra, you'll know why I keep confusing the word coset with equivalence class. In this case, we should call it an equivalence class and not a coset. Okay, so you take the equivalence class that contains that fraction. Okay, so what we want to do then is we want to prove firstly that this addition rule that I've defined on this set of equivalence classes of fractions is actually going to be well defined, and then what we want to prove is that it is actually going to obey the axioms of an abelian group, because remember, if we're trying to define field operations on this set of equivalence classes, we need the addition operation to be an abelian group operation. Okay, so well-defined firstly, so that's our first big check, because if it's not well-defined, then we don't even want to bother trying to check that it obeys the axioms of an abelian group, because if it's not well-defined, it's useless. Okay, so what do I mean by well-defined? Well, the big problem is that I have told you to take a representative from here, take a representative from here, construct this new fraction in this way, and take the equivalence class that contains that new fraction. The question is, what would happen if I took a different representative from here, a different representative from here, and then constructed the fraction for those, and then took the equivalence class that contains that? Would I end up with the same answer? Okay, so well-defined means that if you give me two equivalence classes of fractions, and then I defer the task to two other people of finding what the answer to those two equivalence classes added together is equal to, will those two people always come back to me with the same answer, regardless of which representatives they pick to use from the two equivalence classes? Okay, right. So what we want to do then is we want to take another representative from this equivalence class here. Okay, so let's take the fraction a prime over b prime, and let's take another representative from this equivalence class here, c prime over d prime, and let's construct the fraction that we get from these two. So we'll get the fraction a prime times d prime, plus, and then we multiply these two together, b prime times c prime, and that would all be over b prime times d prime, like so. Okay, so this is the fraction that we get, and what we want to do is make sure that the equivalence class that contains this new fraction here is the same as this equivalence class here, i.e. what I want to make sure of is that these two things are related to one another. Okay, so what I know is that a over b is related to a prime over b prime because they're in the same equivalence class. I also know that c over d is related to c prime over d prime because they're in the same equivalence class. What I now want to prove is that a prime times d prime plus b prime over times c prime over b prime times d prime is in the same equivalence class, is related to a times d plus b times c over b times d here. I want to prove that these two are in the same equivalence class. Okay, so from this statement here, I want to prove this statement here. So how am I going to do that? That is what I need to do if I'm going to prove that this is well defined. I want to show you that although you might get different fractions here, the actual equivalence class that contains them is exactly the same. So the answer is always going to be the same, basically. Okay, so let's write out then the conditions that I'm going to get from this. Okay, so if a over b is related to a prime over b prime, then that means that a times b prime, the numerator here times the denominator here, is equal to b times a prime. Okay, so this is the statement that I get from that. Okay, if this is true, equivalently I can get that c times d prime is equal to d times c prime, and from these two things I want to prove that the condition that I need to prove for this to be true is going to be true. So what condition do I need to prove in order for this to be true? Okay, well I need the numerator here times the denominator here, so let's write that down. Whoops. A prime times d prime, okay, plus b prime times c prime. Okay, so that's the numerator from this one on the left here. Okay, like so. Times the denominator here, which is b times d here. Okay, so that's the denominator from this one on the right here, so I'll colour that in red. I need to prove that that is going to be the same as if I take the denominator from here, b prime times d prime. Okay, and again I'll colour code this in, so here it is in orange, and multiply it by the numerator over here, and I'll colour the numerator over here in purple. Okay, so I'll put that in here, ad plus bc. Like so. Okay, so to try and prove this, and I'm sure stress, I'll put a question mark there. We don't know this is true, I'm trying to prove this is true. Okay, if I can prove that's true, then this is true, and therefore addition is well defined. Okay, so let's multiply both of these brackets out using distributivity that will work in the domain here. Okay, so we will apply distributivity here and we'll get a prime d prime times bd, and I'm using the fact that multiplication obeys associativity in an integral domain, so I don't need to bother putting brackets in. I can just have 4 things multiplied together in a line like that. Okay, plus b prime c prime times bd. Okay, so that's the left hand side here, and now let's expand the right hand side, so we'll keep the question mark there, is equal to b prime times d prime times a times d plus b prime times d prime times b times c. Okay, now I need to prove that if these two things are true, this side is equal to this side. So I need to try and modify this side to turn it into this side. Now, a big help to me is the fact that multiplication obeys commutativity in an integral domain. Remember, an integral domain is a non-zero commutative ring, which also obeys that special property of integral domains that any 2 non-zero elements will multiply together to give a non-zero answer. Okay, so we can use commutativity of multiplication in an integral domain to help us along here. Okay, so how am I going to do this then? Which bit are we going to turn into which? Well, look at this portion here, and look at this portion here. Okay, both of those look very similar. D prime and D, both of them have D prime and D in. The difference is that this one has A prime times B, and this one has B prime times A, but look, A prime times B is this side here. Okay, so I'll just get some more colours here. So A prime times B is this side here, okay, and on the other side we've got B prime times A, that's that side there, okay, so just by substituting in for A times B here, sorry, A prime times B here, and I'm just applying commutativity and associativity of multiplication here, I can substitute in A times B prime and therefore turn this one into that one. Okay, so this portion is exactly the same as that one because of this condition here. Excellent. And now let's do the equivalent thing over here. So now let's look at, and I'll get a different colour rather than yellow again. Let's look at this one here and compare it to this one here. So which bits do they have in common? They both have a B prime here and a B. Okay, so B prime and B over here. The difference now is that this one has the C prime D here, okay, which is this bit here, and this one has D prime C here, which is the same as this. Okay, so again I can substitute in for C prime D here, C D prime, and turn this into this. So again those two things are equal to each other, and that's why this is true, that this side is equal to this side, and therefore this one is related to this one, and therefore addition is well defined. I can take any two representatives from these equivalence classes here, construct this fraction in this way using addition and multiplication in the initial integral domain, and then take the equivalence class that contains that fraction, and that will be my answer in the fraction field. And addition is now well defined. Excellent. So now what we need to do is make sure that the addition actually obeys the axioms of an abelian group. Okay, now this is quite easy, okay? There's nothing difficult in what we're about to do, but it is a little bit dull, okay? But still, it will give us some good insight into how the field of fractions works, so we will still do it. Okay, so let's go through the 5 axioms of an abelian group and make sure our addition obeys the 5 axioms. Okay, so axiom number 1. Axiom number 1 is closure. Okay, so it must be the case that when I add one equivalence class to another equivalence class, I get another equivalence class back again. I get something back within the set. Okay, so if I write this out, if I take one equivalence class, okay, and I'll put a for all there, so for all A over B bar and all another equivalence class here, C over D bar, which is an element of my fraction field, I have to make sure that when I add them together, A over B bar plus C over D bar, that I get something that is back in the fraction field, capital F here. Okay, and this is addition in my fraction field according to the way that I have just defined it. Okay, so why is it going to be true that I always do end up with something back in the fraction field? Well, we've discussed this already, okay? This thing that you construct here, when you take a representative from here and a representative from here and construct this new fraction, this will always be a fraction, okay? AD plus BC will be some element of the domain, so the numerator will be an element of the domain, and B times D here will be an element of the domain, and it won't be 0. Okay, provided that B and D are not equal to 0, and again I'll stress we are using the fact that it is an integral domain there. Okay, So you will end up with another fraction, and therefore that fraction will be in some equivalence class, and therefore you will end up with another equivalence class as your answer. Okay, so yes, when you do add two equivalence classes of fractions together, you get another equivalence class back with this definition of addition that I have built here. Okay, so closure is obeyed, so that's fine. Axiom number 2 now, and to not waste space, I'll put it here. Okay, so axiom number 2 is associativity. Okay, now this is going to be very, very nice, very, very easy. Okay, it will just follow from all of the axioms that worked on the integral domain. Okay, so let me show you this. So we're now going to take 3 equivalence classes. So let's take 3 arbitrary equivalence classes. So let's say we've got A over B bar, and then we've got, whoops, I was about to write B again, C over D bar here. And then finally we'll have E over F bar here. Okay, so I've got 3 equivalence classes from my fraction field capital F. What I want to make sure is that this addition obeys associativity, i.e. it doesn't matter where I put the brackets. So if I want to consider what these 3 equivalence classes added together are going to be equal to, so A over B bar plus C over D bar plus E over F bar, like so, it doesn't matter where I put the brackets. So I want to prove that if I put the brackets like that, it's going to be the same as if I put the brackets in the other way. So A over B bar plus, and now I have the brackets here, C over D bar plus E over F bar, like so. Okay, and this addition here is addition in my fraction field. Okay, so this isn't difficult, it's just boring. Okay, so all I have to do is take both sides, develop them a little bit, get them in terms of operations on my integral domain, pick sensible suggestions for the equivalence classes here, and then do it for both sides and show that they're equal to one another. So I will just do this. Okay, so firstly let's do this portion and this portion here. So A over B bar plus C over D bar, we take a representative from here, representative from here. Let's take the most obvious representative, so we'll have AD plus BC over BD, so we construct this new fraction and take the equivalence class that contains it. Okay, so that will be the answer to this portion here in green, and what we'll still have to do is add this onto E over F bar, like so. Now remember, that addition there is addition in my fraction field, whereas all the operations here are in my domain, capital D. Okay, now let's do it for this side over here. Okay, so that's equal to the left-hand side here. Now let's work on the right-hand side here, and I'll just put a question mark there. Okay, so C over D bar plus E over F bar, adding those two together, we'll get the numerator times the denominator here, so we'll get C times F, plus the denominator here times the numerator here, so plus D times E over D times F, so we've constructed this new fraction here, and then we'll take the equivalence class that contains that. Okay, so this one is this portion here. Okay, and then what we'll do is we still have to add the equivalence class that contains the fraction A over B onto that here. Okay, so now let's work out both of these sides further. Okay, so let's add this one to this one here. So what we'll do is take the numerator here, multiply it by the denominator here, so we'll get AD, and I'll just apply distributivity because we know that works in the domain. Okay, just to speed this up a bit, skip a few steps. Okay, so we'll get AD times F plus BC times F. I hope your ring theory is good enough that you can cope with this now. Okay, plus the denominator here times the numerator here, so we'll get BD times E. And again, I'm using the fact that I have a bit of intuition for how associativity and commutativity and things like that work with multiplication and addition, so that I don't have to put in brackets here. Okay, so it would be a total nightmare, by the way, if you actually try to do this completely rigorously. Okay, so if you try to actually put in brackets, it would just be a nightmare. Okay, so you have to use the fact that we've developed some intuition for ring theory and simplify it down in this way so that you don't put brackets in there. Okay, because you know associativity works. And then we'll have BDF on the bottom here. Okay, so now we'll take the equivalence class that contains that fraction. So here is the answer to the left-hand side here. Okay, and again I should stress I took a sensible representative from here. I took the representative E over F. Okay, and I'm picking the same representatives on both sides, note. Okay, so if I now want to add these two together, I take a representative from here, take a representative from here, and construct the new fraction, and then take the equivalence class that contains that. So which representatives am I going to pick? A over B, obviously, and then this thing again. Okay, so I'd be mad not to. I could do it with different representatives. I proved that it's well defined, so I could do it with different representatives, but why on earth would I? Okay, so as long as you pick the same representatives from each of these equivalence classes on both sides, this becomes pips. If you did try and do it with different representatives, you'd run into horrendous difficulties. Okay, so then what I'm going to do is take the numerator here, multiply it by the denominator here, so we'll get A times D times F, plus the denominator here times the numerator here. Again, I'll apply distributivity straight away. B times C times F, plus B times D times E, over B times D times F, the two denominators multiplied by each other, and then we'll take the equivalence class that contains that fraction there. So here is the right hand side. Now, because I made sensible suggestions, because I used the same representatives on both sides, and because I used a sensible representative from these things here, okay, it turns out that the two representatives that I have of the final two equivalence classes here are exactly equal to one another. Now let's just check this. ADF plus BCF plus BDE over BDF. Okay, so I'm asking on the left hand side for the equivalence class that contains this representative, okay, and on the right hand side I'm asking for the equivalence class that contains the exact same representative. Of course those are exactly the same equivalence class, so these two ways of doing it are exactly equal to one another. And again, I will stress that you do not need to worry about what would happen if you took different representatives from all of these equivalence classes here, okay, because we know it's well defined, so the answer will be the same. It doesn't matter which representative you took. We just took the most convenient that make this easy and simple to prove. Okay, so there is the proof that associativity does indeed hold true. Okay, next. So, axiom number 3 now. We want to prove that there is an additive identity. Okay, so something that will add to all other fractions, or all other equivalence classes of fractions, to give that equivalence class back again. Okay, so I claim that the additive identity is the equivalence class that contains the fraction 0 over 1. Okay, now what other fractions are going to be in that same equivalence class? Okay, so let's think about what other fractions will be in that same equivalence class. So if I've got another fraction that's going to be in the same equivalence class, then it will have to be related to 0 over 1, and what that will mean is that A will have to multiply by 1 to give the same thing as B multiplied by 0, okay, so that would imply that A is equal to 0. Okay, so in fact this equivalence class contains all fractions where you have 0 in the numerator. Okay, so if I just actually write this out explicitly as a set, it'll be all things of the form 0 in the numerator, and then you can have whatever you like in the denominator, provided of course that it isn't equal to the additive identity. Okay, so this is what this equivalence class actually looks like. It's all the fractions where you have 0 in the numerator, but then anything else in the denominator. Okay, so this is an equivalence class that will be in our fraction field, and I claim this is my additive identity. And what I want to show you is that is true. So let's take an arbitrary other equivalence class from my fraction field. So here I have some arbitrary other equivalence class A over B here, bar the equivalence class containing the fraction A over B, and what I'm going to do is add it to this equivalence class, which is the equivalence class containing the fraction 0 over 1. Okay, so plus A over B bar here. Okay, and again I'll stress that this is addition in my fraction field in the way that I have defined. Okay, so the way that I'll do this is take a representative from here, take a representative from here. I could pick any representative from here and any representative from here, but let's take the most obvious ones. So let's take the representative 0 over 1, and let's take the representative A over B. Construct the new fraction, so I'll multiply the numerator here by the denominator here. I'll get 0 of course, so don't bother there. Then I'll take the denominator from here, multiply it by the numerator there, I'll get A back again, so the numerator will just be A, and then I'll multiply the two denominators, and of course that'll just give me B. So here I'll take the equivalence class that contains the fraction A over B. Okay, so of course I have taken this equivalence class and added it to this equivalence class and got that equivalence class back again. Okay, and you can imagine that if you did it the other way around as well, so swap them around and do it the other way around, that the same result will be true. So indeed, this equivalence class is my additive identity in the fraction field. It's the equivalence class of fractions which will add to all other equivalence classes to give those other equivalence classes back again. Okay, so there's my additive identity. Okay, now axiom number 4, I want to make sure that there are additive inverses. Okay, so if I take an equivalence class of fractions here, so a over b bar is an element of the field, I want to prove that there exists an additive inverse. So I want to prove that there exists what I'll call negative a over b bar. Okay, so the additive inverse of this equivalence class here, okay, such that the two can add together to give the additive identity, so such that a over b bar plus the additive inverse of a over b bar, and I'll stress this is just a symbol for the additive inverse of this element here, will give me the additive identity 0 over 1 bar. Okay, right, so this is what I want to prove. Okay, so how am I going to do this? Well, I'm going to just tell you what the additive inverse of an equivalence class of fractions is going to be. Okay, so this equivalence class of fractions, this is the equivalence class that contains the fraction a over b. Okay, I claim that its additive inverse will just be the equivalence class that contains the fraction, the additive inverse of a in the integral domain over b. Okay, so just take the equivalence class that contains this fraction. Now this fraction will exist, okay, because a will have an additive inverse, okay, so this will be a fraction, and it will be in some coset, some equivalence class. So you can find this equivalence class, and let's now see what would happen if I added this equivalence class to this equivalence class. So let's now ask, what is a over b bar plus negative a over b bar, the equivalence class that contains this fraction? Okay, and we're doing this addition in the fraction field here. So what we'll do is multiply a and b together in the integral domain, the numerator here with the denominator here. Okay, so we're constructing the new fraction. I should stress, again, really what we're doing is taking a representative from here, taking a representative from here. I might as well take this representative and this representative, the representatives after which I've named these equivalence classes. Okay, so I'll multiply a by b. Okay, then I'll multiply b by negative a, so I'll get b times negative a. Okay, and then I'll multiply the two denominators here, so I'll get b squared. Okay, now I'll take the equivalence class that contains that. Now, a times b, its additive inverse is b times negative a. You can prove that easily with distributivity. Just factor out the b, and then you'll have a plus negative a. That will give you 0. B times 0 will give you 0. So overall, this will be 0 over b squared. It will be the fraction 0 over b squared. We want the equivalence class that contains that. Now, what is the equivalence class that contains 0 over b squared? Well, all elements of that form, 0 over something that is not equal to the additive identity, and of course b squared will not be equal to the additive identity provided that b was not equal to the additive identity, and of course that will be true. Okay, so it will be something of this form here, and therefore it will be in the same equivalence class as 0 over 1, so we'll have got back to the additive identity equivalence class of fractions. Okay, so that's absolutely fine, and now what we want to prove is commutativity, axiom number 5. Okay, so we want to prove that if we take any two equivalence classes of fractions, a over b bar plus another equivalence class of fractions, c over d here, okay, we want to prove that it's the same if you do it the other way around. Okay, so if you take c over d bar plus a over b bar, okay, add these two equivalence classes of fractions the other way around, I want to prove that the answer is exactly the same. Okay, so addition in my fraction field needs to obey commutativity. Okay, so how am I going to do this? Again, just work out both sides and show that they're equal to one another. So to do the left-hand side, I take a representative from here, take a representative from here. Okay, I'll use the representative a over b from here and c over d from here. Okay, and then I'll produce the fraction from these. Okay, so ad plus bc over bd, and then take the equivalence class that contains that. Okay, remember all the operations here are in the initial integral domain, capital D. Okay, then on this side, again, I take a representative from here, take a representative from here. You could take any representatives, but why on earth would you take anything but the same representatives you took over here? Okay, and then if you add them together, what you want to do is add the two representatives together, produce this new fraction from them, and then take the equivalence class that contains that. So the new fraction you'll get is c times b plus d times a over d times b, and then you'll take the equivalence class that contains that. But I claim that those two fractions are exactly equal to one another because the denominator is exactly the same. B times d is d times b because of commutativity of multiplication in the integral domain. Okay, and because of commutativity of multiplication and addition in the integral domain, the numerator is always also the same. So in fact, these two representatives that I've got here are now exactly the same fraction. So again, I'm asking for the equivalence class, equivalence classes that contain the exact same fraction. So indeed, these two equivalence classes are going to be exactly equal to one another. Okay, so the answer here is the same as the answer here. Addition of these equivalence classes of fractions does indeed obey commutativity with this definition of addition. Okay, so to summarize what we have done then, okay, in this video we have defined addition in our fraction field. Okay, and the way that we have done it is we've said if you have one equivalence class of fractions, the equivalence class that contains a over b, and you've got another equivalence class of fractions, this equivalence class that contains c over d, take a representative from each of these and use them to construct this new fraction, okay, which has this form. So if you took the representative a over b and c over d, you'd construct this fraction here using the numerators and denominators from those two representatives. So ad plus bc over bd. And all that requires you to know is the operations on the initial integral domain. The answer is then, of course, the equivalence class that contains this new fraction that you've constructed from your two representatives of these two equivalence classes of fractions that you wanted to add together. Okay, and what we've shown is that this is a well-defined addition operation and that it obeys the 5 axioms of an abelian group. Okay, so this is going very well. We'll have a break here, and in the next video what we'll do is define the multiplication rule on the fraction field, and we'll prove that it obeys the axioms of a field.